welcome back. We're in Lecture 5, the second segment, and the last segment of Lecture 5, and the last segment before we're ready to jump into inferential statistics. And the topic of this segment is sampling. As you'll see, the important topics to take away are the idea of sampling error and standard error, which leads us to a more abstract concept of probability histograms, ending in this very general concept, the central limit theorem, which is essential to understand before doing inferential statistics. And I should say, before I start this segment, I've taught statistics for a long time, and I know that this last segment where we get to the probability histograms and central limit theorem is where a lot of students have trouble. So you might want to review that section of this segment over and over just to get that down before we move to inferential statistics. So to make this palatable, we'll go back to wine tasting. Remember the 4 wines that we had our wine experts taste? We've used this example a couple times now, so I can zip through it quickly. The 4 wines demonstrated 4 different distributions. What I'd like to do with these wine ratings today is zoom in on the normal distribution red truck. So we're going to take a closer look at red truck. And suppose that there are only 300 certified wine experts in the entire world. So the population of wine experts is 300. And let's further assume that those ratings for red truck in the population are perfectly normally distributed, as they were in our sample of 30. So if we look at the population in a histogram, this is 300 certified wine experts, that's the population. They're exhibiting a perfectly normal distribution with a mean of 5.5 and a standard deviation of 2.2. Now, we probably can't always get our hands on all 300 of these wine experts if we want to test out different wines, right? We probably want to get a random sample. As we've been doing, we've been getting random samples of 30 of them. So here's what a random sample of 30 of the wine experts looks like for red truck. And you see that this sample is not perfectly normal. There's a little bit of a bump here around 6, 7, 8. But overall, it's not too bad. It's relatively normal. You see that the mean is a little bit higher than the population mean. So here we have a mean of 5.93 instead of a mean of 5.5. So there's a little bit of sampling error. The sample doesn't match the population. So what if we want a bigger sample? We don't want so much sampling error. Let's get a random sample of 100. Now it's looking pretty close to the population. It's not perfectly normal. See, there's this little blip down here. So it's not perfectly normal, but it's darn close. And the mean is very close to the mean of the population. So the mean for this sample is 5.47. The mean for the population was 5.5. So there's still a little sampling error, but very slight. Now let's go in the other direction and take a small sample, just 10 of the wine experts. Now you see we get a very funky looking distribution. It doesn't resemble the population much at all. And the mean is 6, whereas the mean for the population was 5.5. The standard deviation is much lower. So now we're experiencing a lot of sampling error because our sample is so small. That's the idea of sampling error, is it's simply the difference between the population and the sample. And we always have to deal with this whenever we engage in this process of trying to get a random and representative sample from the population. But the problem is we typically don't know how big the population is, and we typically don't know what the population parameters are. In this example, we do because I made it up. Right? I just said, let's assume there are 300 wine experts, and let's assume that the mean on Red Truck was 5.5. But let's take my own research, for example. I'm looking at cognitive ability in all healthy young adults. That's a large population. I can't even approach that in my samples. So I'll typically experience probably a lot of sampling error. But I don't know how much. From study to study, I don't know how much sampling error I'm experiencing. So we need to come up with some way of estimating how much sampling error we have in each study we do. So how do we do that? Well, just looking at that little example with the wine experts, sampling error clearly depends on the size of the sample, so N, but also the degree of variance in the population. So if there's a lot of variance in the population, then most likely we'll have more sampling error than if there's a small degree of variance in the population. So those are going to be the two main estimates that we put in to get at our overall estimate of sampling error. So I'm going to introduce a new formula and a new concept here, and one that will be essential as we move forward in inferential statistics. And that's the idea of standard error. So standard error represents the overall average amount of sampling error in a particular study. And the way we calculate that is we look at the standard deviation in our sample and we divide by the square root of n. So standard error, how much sampling error do we expect on average? Depends on the size of the sample, depends on how much variability we see in our sample. So this should be pretty straightforward just conceptually. The bigger the sample, the less the standard error. And if you look at this, n is in the denominator of this equation. So as n goes up, standard error goes down. Okay? As n approaches the population, sampling error goes down. So let's go back to histograms for a moment. Remember, if a histogram is perfectly normal and we have normalized scores, if we standardize to z-scores, then we know a lot about that distribution. So let's bring back that graphic of the normal distribution. If it's perfectly normal and we've standardized the units, then we know what percentage of scores fall in certain regions of the distribution. So remember, it's normal, meaning it's perfectly symmetrical. So 50% of the distribution falls below the mean, 50 falls above the mean. We also know that 68% of the distribution falls between one standard deviation below and one standard deviation above. The trick now, and this is the point where a lot of students fall off the cliff, so pay attention, is the trick now is instead of thinking about this as representing a histogram and a distribution of individuals, we now have to think about this as representing a distribution of samples. What do I mean by that? That's called a probability histogram. And the first probability histogram we'll encounter is this distribution of sample means. The idea here is, imagine I went out and I sampled the wine experts. Take this first example with an n of 10. Imagine I did that over and over and over and over again. I did it once here, and we saw that the mean was about 6. Right? It was pretty far off the mean for the population. Say we sampled another 10, another random sample of 10. Their mean wouldn't be exactly 6. It would be somewhere around 5.5, but it might be a little lower, it might be a little higher. Each time I sampled, I'd get a different sample mean. And there'd be a lot of fluctuation if my samples only had 10 wine experts in them. But if I went up to 100 and I sampled repeatedly, then there'd be less fluctuation in those sample means. So then, if I plotted all my sample means, what we would observe is a normal distribution, but the width of that distribution would be largely influenced by the size of the samples that I took. If I took small samples of 10, then the distribution of sample means would be wide, right? There'd be a lot of fluctuation. So I'd have a wide distribution of sample means. But if my samples were large, 100, then we'd only have a little bit of fluctuation. That's where the idea of standard error comes in. Standard error is this distance right here, from the mean to one standard deviation above and one standard deviation below. It's one standard deviation in the distribution of sample means. I know that's a mouthful, so you might want to replay that. It's one standard deviation in the distribution of sample means. So this distribution of sample means, again, I know from doing this class many times, is hard for students to wrap their head around because it's a hypothetical. When I do my research, I don't get repeated samples. I get one sample, I do my study, I get my statistics on that, I get my inferential statistics, and I move on. I don't have time to do repeated samples. But I rely upon this idea of repeated samples to do my inferential statistics. So let's talk about this idea of this distribution of sample means. We assume it has certain characteristics. So again, it's hypothetical. We don't know the dimensions, but we can estimate them. We'll assume that the mean of the distribution of sample means will be equal to the mean of the population. So again, think about the wine experts and the wine ratings. If I sampled repeatedly samples of 100 wine experts, each sample won't have a mean of exactly 5.5. Sometimes I'll get 5.6, sometimes I'll get 5.4, I might even get something as high as 5.8. They'll fluctuate, right? But overall, the mean of those means, or the mean of the distribution of sample means, should fall right around the mean of the population. What about the variance, or the standard deviation? Well, that's what I was just talking about with standard error. That's largely influenced by the sample size. So the variance in that distribution of sample means will be equal to the variance in the population divided by the size of the sample. And that's exactly where we get that estimate of standard error from. Here, I'm using sigma because I'm talking about population parameters. Remember, sigma squared is the population variance. I'll use SD squared to refer to the variance in the sample, and standard error to refer to the standard deviation of the distribution of sample means. This, again, is why this is a place where students start to get lost, because there's a lot of similar notation for very different concepts. Again, there's variance in the population, sigma squared. There's variance in the sample, SD squared. And there's a standard deviation of the distribution of sample means, standard error. Finally, the shape of this distribution of sample means will be approximately normal, even if the distribution in the population isn't normal. And again, we don't know most of the time if the distribution in the population is normal. But we will typically get a normal distribution in the distribution of sample means as long as we're sampling large enough samples. So to recap this piece, this sort of the most confusing part is we have variance in the population, we have variance in the sample, and we have variance in this hypothetical distribution of sample means. All of that together comprises what's known in statistics as the central limit theorem. And this is the sort of central piece that we need to move forward to do inferential statistics. So sort of everything we've been doing leading up till now brings us to this point, the central limit theorem. And this was developed by statisticians and is used in applied statistics to do inferentials. The three main principles are what we just walked through. So the mean of this hypothetical distribution of sample means is the same as the mean of the population. The standard deviation of the distribution of sample means can be estimated, and we're going to estimate that to be standard error. So this is the formula talking about it in the general sense, but what we'll do is calculate standard error, and it's the standard deviation over the square root of n. So that's just taking the square root of that formula and not putting it in population parameters, but putting it in sample statistics. And finally, we can assume that the shape of that distribution is normal as long as we have samples that are large enough. Here I said samples equal to 30 or greater. Some people would be a little more liberal than that and say if you have samples of even 20 or greater, you'll get a normal distribution. Let's be safe and assume 30. You'll get a normal distribution in your distribution of sample means. So to wrap up this section, the most important topics to take away are, again, this idea of sampling error. So whenever we conduct studies, we typically can't get the entire population, so we get a sample. The problem is we don't know how much sampling error we're experiencing. So we have to estimate that some way. And the way we estimate that is to rely on the principles of the central limit theorem and calculate standard error by looking at the standard deviation in our sample and the size of our sample. And very simply, the amount of standard error that we have is directly related to the size of the sample. Bigger samples, less standard error, and that's preferred. I also introduced this idea of probability histograms. Again, that's a little bit difficult to wrap your head around because we're used to looking at histograms that represent distributions of individuals. But now we'll look at histograms that represent distributions of samples. And the first one we'll deal with is that distribution of sample means. And that allows us to dive into inferential statistics, which we'll do in the next lecture.